Hello everyone, welcome to this session. My name is Sudipto Das. I'm a principal engineer at AWS working on Amazon TimeStream. For the next 1 hour, I'm going to walk you through a deep dive on Amazon TimeStream. We'll start with talking about the key value propositions of Amazon TimeStream and where you should consider using TimeStream. Then I'm going to walk you through some of the new features that we have launched in 2021, starting with the features at re:Invent, but also briefly talking about some of the features that we have launched throughout the year. I'm going to talk you through a few diverse use cases to give you an idea of how our customers are using TimeStream in a variety of different scenarios to enable different application use cases. And at the very end, I'm going to talk about why Amazon TimeStream is purpose-built for time series workloads to provide you a brief overview of TimeStream's architectures and some of its performance characteristics to help you understand and rationalize why we are doing some of these things and how we do some of these things. So as we get started, time series data is everywhere, all around us. If you look at any industry segment, application category, you would find data that is tagged with time, metrics that are changing over time. And that is what fundamentally time series data is. You would see industries trying to tap onto that to improve their overall efficiency and understand their real-time productivity as well as performance. You would see energy companies trying to predict future energy consumption as well as understand their different energy consumption across the fleet of devices as well as across the cities. Monitoring in DevOps, monitoring a fleet of servers, your fleet of applications, your fleet of devices, inventory control, inventory management, optimizing your supply chain, in agriculture, so on and so forth. Given that time series data is so widespread and it has been there for a very long time, so one might ask the question, what's unique about these time series workloads and why do we need a purpose-built database for these time series workloads? So let me walk you through some of the scenarios that we see again and again across many of these time series use cases, which told us that the customers wanted a purpose-built time series database. One of the common characteristics that we see across many time series use cases is high throughput ingestion along with concurrent query. You have millions of devices that could be emitting data, hundreds of millions of video streaming sessions emitting data. You want the data to be streamed into your time series database to give you real-time insights on what is happening in your fleet, how your users are interacting with your system. And you could have hundreds of these concurrent queries running on your real-time recently ingested data, as well as comparing past historical performance to what you're observing at this point in time. When you have these gigabytes of second of ingest, as well as hundreds or even thousands of concurrent queries from different dashboards, from your analytic operational systems coming in, this is where your instance-based systems start tipping over. Your dashboards become unresponsive, and that's the last thing you would want from a system or a service that you are using to observe what's happening in real time. Another aspect is high time series cardinality. We have customers tracking millions of video sessions, hundreds of thousands of devices, emitting hundreds of metrics. That translates to about billions of time series and trillions of events that can be emitted at a given day. That is the scale that these services need to be able to scale to, as well as provide you the flexibility so that if your use case is much smaller, you can still benefit from some of the scaling characteristics as well as some of the automatic resource management characteristics. If you have ever worked with a relational database or one of the databases that works with a rigid schema, you would know how hard it is to manage the schema as your applications evolve. A lot of the time series use cases are for devices that are deployed across the world, IoT sensors that get deployed with disconnected operation. You would want a system that allows you to iterate on your application and evolve your schema seamlessly by having flexible schema evolution support. And this came up repeatedly across hundreds of customer conversations that they don't want the complexity of managing a rigid schema. You would want to have fleet-wide analytics and fleet-wide insights of what is happening across your service, what's happening across your fleet of devices. But along with it, you also want the ability to drill down into individual devices if the need arises. So you would want to track aggregate information. If something is out of order, you see some anomalous behavior, you would want to quickly drill down to identify where it is. So tracking data at these different granularities and providing you quick insights, that's significantly important. For the broad class of applications that are being deployed, enterprise-grade security, encryption, fine-grained access control, these are table stakes requirements for many of these enterprise applications that we see. And last but not the least, time series workloads often are inherently bursty. You have an event going on, hundreds of your users might be refreshing your dashboards, you can have a spike of queries. You have new devices that got onboarded, you have a new deployment that went in, or a lot of user activity from you. If you are tracking your users, there could be a spike of activity on your ingestion. And again, in those cases, you would want automated resource provisioning so your system doesn't become unresponsive when you need it most. To address some of these unique requirements of time series workloads, we built Amazon TimeStream from the ground up as a purpose-built serverless time series database that allows you to collect, store, and process time series data at any scale. It is completely serverless, no instances to monitor, no instances to provision, and no resources to track. It is completely serverless and auto-scaled independently for ingestion, storage, and query. Time series data often requires data lifecycle management. Your most recent data is where a lot of activity is happening, but you also want your historical data to be in the same system so that you can perform your historical analytics. You can compare your most recent statistics with what was happening last week, last month, last year, et cetera. So the ability to support data lifecycle management, where as your data becomes older, it moves into a much more cost-optimized storage format that's built into TimeStream. As your data gets older and you don't need to keep it around, data is automatically deleted, and these are controls that are given to you as a user. And the system takes care of all of the lifecycle management. As I mentioned, flexible schema. So TimeStream gives you a concept of databases and tables, the familiarity of your database concepts, and it gives you a table with columns. But you do not need to define those columns up front. The data that you send is self-describing. It specifies what are the different attributes, and the table schema is automatically derived from the data that you are sending. So think about if you are doing an application rollout, some devices are sending data in your old schema, some devices start sending data in your new schema, not a problem. As soon as the data with your new schema shows up in TimeStream, that is automatically reflected in your table. I talked about this storage tiering that is built into TimeStream, but as a user, you don't need to worry about it. You just focus on your queries. You specify your time range. Depending on what time range and what data your query is accessing, TimeStream will figure out how to get your data across these storage tiers so that you have a seamless experience no matter where your data is, even when your data is moving from one storage tier to another storage tier. It always remains queryable. It has built-in analytical capabilities. It supports the full ANSI SQL select dialect. In addition, we specialize for some of the common time series use cases and functions that many of our customers often use. So we have built-in time series analytics, for example, interpolation, derivative, integral, correlation, and so on. And TimeStream also integrates with a broader set of tools to help you get your work done. This includes integration with ML services, visualization services, as well as data collectors to have your data come into TimeStream. So just to recap the key benefits, TimeStream is fully managed. It's secure by default. The data is always encrypted at rest and in transit. And this is something that you can't even turn off because many customers say that's one of the places they misconfigured the system. So it's on by default. Data is completely durable in TimeStream. As soon as you send a write and we acknowledge the write, we replicate it across multiple AZs, so we stand by that data. And the service is designed to be highly available. So it is using state-of-the-art replication as well as a bunch of other techniques behind the scenes to make sure that even if instances are failing in the background, even if newer versions of the software are being rolled out to the service, you don't see that impact. And the database is always available for you. And we support, it's backed by a 99.99% uptime SLA. You will see that we talk about scale a lot. But one of the important aspects that I want to stress here is TimeStream is really designed for any scale. It provides you the economies at the scale of bytes. As your application grows and as your data volume grows, TimeStream automatically scales with you to take you to exabytes. We have many of our customers who are generating sporadic activity, sporadic ingestion, or sporadic querying. And even at that small scale, you see the benefits of serverless with TimeStream because you only pay for what you use, as opposed to an instance-based offering where you have to provision your instance for your peak workload, and you pay for it no matter if you're using it or not. So that's the economies of serverless. And then as you scale, if you have a sudden spike of activity, we are scaling resources in a matter of minutes for you in order for you to serve those requests. So these are the key benefits that allows you to just focus on your application. So from our perspective, we want you to focus on how you want to model your data, send us the data to the TimeStream endpoint, how you want to model your queries, send us the queries to the TimeStream endpoint, and we take care of the rest of the details, and you pay for only what you use. And on top, providing a familiar and flexible SQL query interface means that you don't need to learn yet another language or yet another way to interact with your workloads. And your familiar tooling and your familiar set of tools that you use can be used in conjunction with TimeStream as well. So as many of you know, TimeStream launched in general availability in 2020. So 2021 has been a busy year for us. We have launched several new enhancements. I'm going to start with 3 features that we launched this week at re:Invent, and then I will also talk about some of the other enhancements that we did throughout the year. So these 3 features that we launched for re:Invent has been to make TimeStream faster and more cost-effective for time series data processing use cases. And this is what we hear from our customers. They love the serverless aspects. They want TimeStream to be faster. They want TimeStream to be cheaper. The first feature that we announced at this re:Invent is what we call multi-measure records. We see many of our customers are emitting metrics where a single device is emitting multiple different metrics at the same time instant. In the current data model, you would store one metric per row in time stream or per record in time stream. This new data modeling provides you a cost-effective way to model your data by allowing you to store multiple metrics in the same time series record, assuming they are coming in from the same device and the same timestamp. You can store hundreds of metrics within the same time record, same time series record, and that gives you the efficiency from a cost perspective. Many of our users use time stream and time series data and to power their operational dashboards. These operational dashboards are loading hours, weeks, and sometimes even months of data. Hundreds of concurrent users are loading those dashboards, and sometimes these dashboards have tens or hundreds of even panels or graphs that are being rendered. As you are repeatedly refreshing this dashboard every 5 minutes, every hour to understand how your recent data is looking, behind the scenes you are sending queries to TimeStream, and depending on your data volume and data sizes, that could result in latency as well as cost for you. But what we realized is many of these dashboards are often tracking aggregate information that you could potentially pre-compute. So this year's reInvent, we launched a new feature which we call Scheduled Query that allows you to pre-compute many of these queries that power your most frequent dashboards, so that instead of those queries going over raw data and repeatedly scanning it again and again, you could have those results pre-computed in TimeStream as just another TimeStream table that results in orders of magnitude faster dashboard loads, as well as now, because you're pre-computing, you're scanning much, much less data. So that also results in significantly cheaper dashboards. This pre-computation is completely serverless. You define the pre-computation, you define how fast, how often to refresh it. Everything else is taken care of by TimeStream. And the third feature is what is called magnetic store writes. If you are familiar with TimeStream, we have the memory store and the magnetic store. Memory store is designed for high throughput writes, but the magnetic store was immutable. We heard many use cases where there are late arriving data because of disconnected devices. You have an IoT sensor out in the field, it hibernates for a few months, comes back online after a few months. You don't want to lose that data in case your memory store retention is configured for a few hours or a few days. You might discover a bug in your application and you want to do data correction. If you discover it in the memory store, in the data that is in the magnetic store, you don't want to be able to lose out on those fixes. So with this launch, we are opening up our magnetic store for writes, for primarily catering to the late arriving or data correction use cases, so that you can configure your memory and magnetic store based on your performance requirements rather than your late arriving data requirements, again resulting in significant cost savings from your storage perspective. So let me walk you through some of these features in a bit more detail. I mentioned multi-measure records, right? So let me start with an example. So here we have a server that is emitting multiple different metrics. You can see here that the metrics getting emitted are CPU, memory, disk IOPS. There are some double values that are getting emitted. And as you would note, they are all coming in from the same host at the same time instant. And this happens across, this is a DevOps use case. This happens across many, many other use cases as well. So with this new data model, you can now start modeling them in the same time series record. So as you can see here, it is evident that a lot of the repetition in your storage got significantly reduced. We allow up to 256 records to be batched in the same, 256 of these metrics to be batched in the same time series record, which means that now you're on the right path. The batching that we support on the write record API is also significantly improved. That improves the number of threads or the efficiencies of your ingestion. The storage benefits are clear already because the dimensions are not duplicated, the timestamp is not duplicated, so you get a much more compact representation, and the storage benefit shows up on both the memory as well as the magnetic store. One of the other things that also happens associated with this data model is the ease with which you can write your queries when you are accessing multiple different measures in your query. In this specific example, we started with the single measure data model. All you are doing in this query is you're comparing two different metrics that are emitted at the same timestamp, and you are trying to figure out which of those metrics was a bottleneck. Was it CPU? Was it memory? The actual comparison is happening in the case statement at the last select statement. But at the top, you will see you had to create common table expressions to align these two measures that were emitted and stored as different rows, and then you perform a join. These queries now become significantly easier to write. Whenever you are touching multiple measures, they are just different columns in the same row, and you could just access it at different columns. In addition to these benefits, the measures time stream supports a richer set of data types. So you could store measures that are double values, 64-bit integers called big int, varchars, strings, booleans, and also timestamp. So we see repeatedly, we saw customer use cases where customers want to store multiple timestamps in the same record. Now you can have these timestamps stored as your multi-measure records. So for example, in addition to the attribute on which you are indexing on, you could store future timestamps, past timestamps, any other logical timestamp that your application wants to monitor. So in summary, this multi-measure feature improves your overall costs, ease of writing queries when you are writing multi-measure queries, and it also lowers in the query latency in many cases because simpler queries are faster to execute as well. So we have several different example data sets that are out there in our GitHub repository for the time stream tools. You will see one of those data sets is a perf and scale data set that we use to talk about time streams performance and scale characteristics. So that data set corresponds to a DevOps use case. A server emits about 22 different types of data. It is emitting metrics with 20 different metrics. It is emitting events. So on an average, you would see there are 10 to 15 different metrics that are emitted. In that data set, as you move from the single measure record to the multi-measure records way of modeling, what we observed was about 30 to 50% lower costs for data writes. This is due to the better batching support. You could ingest about 10x more metrics per batch. That means fewer threads to ingest that data. It resulted to about between 6x to 10x lower storage, and that is a very significant reduction in the storage cost. And obviously, the query latency, you would see your benefits may vary depending on what kind of queries that you are running. But we saw cases where you could see up to 3x lower query latency as you move from your single to multi-measure record. And many of our customers have been asking us about storing hundreds of records, hundreds of metrics in the same row. So as you are able to store more and more of these metrics in the same row, your improvements can be even more significant. So the next feature is scheduled queries. As I mentioned, it is primarily targeted for use cases where you have the exact same queries running repeatedly. But as you will see, it provides you a significant amount of flexibility that you can use it for a variety of other use cases that you can think of. So if you have these cases where the same data is being repeatedly read again and again, you could pre-compute the results. And the way it works is that you define a query that you would want to pre-compute. You look at your dashboards, identify what are the aggregates that are computed, how is the data being grouped, and so on, and you specify that exactly as a SQL query, very similar to the SQL query that is running on your dashboard. You specify a target time stream table where these pre-computed results can be stored. So this table is just like any other time stream table. So it has all the properties of a regular time stream table as well. The data will be automatically materialized in that table. You can have different retention periods on that table. So we have customers where they have 1 hour or 2 hours retention on the raw data, but they can have a week of retention on the table that is doing the pre-computation because it is much smaller. So you can have much more data for much longer in your memory stored in the target table, if you so desire. You specify the refresh interval on how you want your pre-computations to be updated. And the way you do it is that a big chunk of the time series data is always moving in time forward. So you are not recomputing the entire data. You are only recomputing the parts as your newer data is coming in. And I'll make it clear through an example. And one of the other benefits of schedule query is it supports the full SQL surface area of time stream. You can have queries with nested subqueries, common table expression, pick your favorite aggregate function, even time series analytics. All of that surface area is supported. And this is unlike many other cases where you can do streaming aggregates on a very narrow surface area. So as we talk to many of our customers wanted the richness to be supported in these pre-aggregates. And similar to all other facets of time stream, it is fully managed, serverless, scalable, highly available, secure, and durable. So you configure again on the business logic. Time stream takes care of the rest. No need to monitor any other, create any other infrastructure to do the pre-aggregates. So let me give you an example. Again, I'm going to use this DevOps data set that I talked about earlier. So this is a data set for a specific scale factor. In this case, we are tracking 500,000 servers across 6 different regions. So as you can see, US East 1 has about 200K, and some of the smaller regions have fewer servers. So this is an example panel that you might have in your dashboard, where you're trying to figure out the distribution of your fleet to understand what is happening. And behind the scenes, it's computing a query like that, where it's using a nested query, it is doing a count distinct, and then aggregating it over the regions. You take a query like this, and what I'm giving you an example here is how you convert it into a schedule query. The one important thing to note here is that in the where clause, in the nested query, you would see a special parameter that showed up. It's called schedule runtime. And this is what allows you to specify what is the time window on which the recomputations are happening. In this case, depending on what value you set to schedule runtime, you would see that the query would go after 1 hour to 2 hours of data in the past. And this is something that you can control, because as you can see, this time range is controlled using a predicate in SQL. You get the flexibility. Similarly, here, what you will see is that we are doing hourly aggregates. You pick which aggregate you want. You can go second aggregates. You can go weekly aggregates, hourly aggregates. That's the flexibility that we support. So the question is, how do we set the schedule runtime? So this is where a schedule expression comes in. So we support a cron as well as a rate expression. So I'm giving you an example of a cron expression here. So this cron expression translates to run this query every 30 minutes at the 30th minute and the tip of the hour. But you will see, as you will see in the detailed documentation, that the cron expression gives you the power of running it the way you want. If you want it to run on every Monday, Wednesday, and Friday at 8 in the morning, you can do that. You want to run it 3 hours past UTC on every day, you can do that. So that's the flexibility that you get from these cron expressions. As you specify this cron expression, let's say if we take the example of this cron expression, what we are seeing is 1st of December at the beginning of the day, that's when the cron expression evaluates to. So that is one of the instances that time stream would execute this schedule query that you define. And based on that timestamp, that is how your scheduled runtime parameter is initialized automatically by the service. So depending on when your query is scheduled to execute, we automatically plug in that timestamp so that you can get this view that every hour you're running this query, or every 30 minutes you're running this query, and looking back for the past 1 hour or 2 hours. The other thing to note here is that even though this query is doing hourly aggregates, you can configure it to run every 30 minutes, or every 15 minutes, or every hour, or every day. And that is driven by your business use case. How fresh do you want your aggregates to be? And you're trading off the freshness with the cost of maintaining these pre-aggregates. And the cost of maintaining these pre-aggregates is very similar to how you would do it in TimeStream. You run a query, you pay for the bytes that are scanned by the query, and then that is generating a result. You write the results into a TimeStream table, you're paying for that write cost. So that is how the schedule queries are actually cost. So no new cost dimension for you. The familiar cost dimensions, you just focus on how you want to pre-aggregate, and then have your, as these queries are running, here is an example of a destination table where the data is getting pre-computed. And now you can use this destination table to power your dashboards. Your dashboards are going to run significantly faster and cheaper. To top it off, this is just like a regular table in TimeStream. And TimeStream supports multi-table queries. So what you can also do is that you can combine combine the data from your pre-computed table with the most recent data in your raw table through a union query, and you can get the best of both worlds, where for your historical data, let's say if you have a weekly dashboard, it's looking at the past week of data. For the last 15 minutes, you go after your raw data, assuming you are refreshing every 5 or 15 minutes. And for the remaining time, you go after the pre-aggregated data. And that way, you can get the union view as well if you so desire. Or if you want the simplicity, you can just go with the pre-computed data. And the raw data is there, again, configured by your retention policies. So if you want to do drill downs on your raw data, it will be stored for you, and it will be configured by the retention policies that you have on that source table. So let me give you an example of how this happens in action. So this is 2 different dashboards that are showing the exact same aggregate statistics, again from the DevOps use case. You will see that the dashboard on your left, that is powered by a table where schedule query is pre-computing the results. And the dashboard on your right is doing the same computation on raw data. As this is going to be a video, I'm going to walk you through that video, but as you will see in the video, I'm going to refresh the 2 dashboards side by side. And if you notice on these individual panels, you will see a spinning wheel that tells you when the dashboard load finishes. So I'm going to play the video. First, I start the dashboard on the raw data. Then I start the dashboard on the schedule query. As you can see, I'm refreshing it multiple times, and it's loading in almost instantaneously. While the dashboard on the raw data, you can still see some spinning wheels in some of the panels. So if you drill deeper into what is happening there, you can see that it is supporting a pretty significant query even on the derived table, so again, the full surface area. But if you look at it, it spent 300 milliseconds to execute the query and scanned only 10 megabytes of data. If I look at the corresponding panel that is going on in the raw dashboard, again, this is the query that was going on. Again, you can take these complex queries and also pre-compute them. This was running for about 36 seconds. So that's about 1,000x improvement in your query latency. And the data scanned is about 700 gigabytes. And that 700 gigabyte transformed into 10 megabytes as you pre-compute. Now here in this case, I was loading the dashboard for just 2 days of data. Depending on your use case, the benefits might vary on what is the latency improvement and what is the cost improvement. But these are the kind of improvements that you can get depending on your use case. So briefly covering magnetic store writes, it is, as I mentioned, it is primarily designed for your late arrival and data correction scenarios. We have the exact same write API as what you would use to write to TimeStream's memory store. So no changes in your application is needed. You just send the data to TimeStream. If it happens to arrive late, TimeStream will figure it out. It will route it to this magnetic store. The only difference between memory store and magnetic store that you will see is memory store gives you almost instantaneous visibility of the writes. But the magnetic store, the writes are applied asynchronously, so you would have delayed visibility of those writes. But the data is delayed anyways to start with. So in most cases, this just works out fine. So no changes again needed from your application's perspective. And you can optimize your storage costs and also enable the newer scenarios that were earlier not possible because you could not do older data correction and so on. And the writes follow the same absurd semantics of TimeStream. So one of the key benefits of TimeStream is it has automatic deduplication and versioning built in. So you can send data with a newer version, it updates the data. If you send the same data again and again and again, it's only written once. If you send data with an older version because it was reordered, it is rejected. The exact same semantics are supported for your magnetic store writes. No changes there. So in addition to these three launches that we did in reInvent, throughout the year, we launched several significant enhancements to TimeStream. And these continuous enhancements were rolled out to you automatically, and that is one of the other benefits of serverless, no versions to manage. So these changes include around compliance. So TimeStream became eligible for many other compliance criteria. From a security standpoint, TimeStream added support for VPCs so that you can now have VPC endpoint, TimeStream's VPC endpoint through private link and communicate with TimeStream from your own VPCs without ever hitting the public internet. We made several enhancements in our schema support. For example, we added support for UTF-8 characters. We increased the length of dimension names, increased the names of measure names, and so on, the table and database names as well. We launched a new region in Frankfurt. On the query side, we added support for multi-table and multi-database queries. So this is what I was referring to earlier, that you could do joins, unions across data across multiple tables, or databases within your same TimeStream account. You could query across them seamlessly. We added a bunch of new time series functions. And by analyzing the workloads and how customers are ingesting data and how customers are using TimeStream, we were able to adapt our automatic partitioning and indexing algorithm that we use in TimeStream to lay out the data. And that makes sure that gives you significant query latency improvements. So we saw across a wide variety of workloads, we saw up to 3x better latency as a result of these optimizations. And we also have a blog that we published recently to talk about some of these benefits and how it was done. And all of this was rolled out to you seamlessly without any need to do any upgrades, without any need to change any applications. Your queries just started running faster. So let me now walk you through some of the use cases. We have a diverse set of customers using TimeStream. The full list is available through our website. And we see these customers across multiple different industry verticals: media and entertainment, energy, consumer electronics, financial services, telecommunication, and so on. And they're running a variety of different scenarios and use cases on us. For example, I talk a lot about IoT. There is application monitoring, fleet management, intrusion detection, and so on. So I'm going to walk you through 4 different use cases to show how customers are using TimeStream in a variety of different ways to meet their requirements. The first one is for monitoring streaming video sessions. So we have a large video streaming service that is tracking their hundreds of millions of users in real time, getting the telemetry for how they are viewing their platform to figure out and optimize the distribution of the video. If a specific deployment, if a specific device, if a specific zip code is having issues, they know in real time. They migrated from an instance-based system running on EC2. And the previous solution kept running into scalability issues that was hindering their business growth. And they had to do a lot of undifferentiated heavy lifting to manage those instances. TimeStream's scaling capabilities, specifically the independent read and write scaling capabilities, as well as the auto-scaling and serverless properties, really help them get rid of some of these undifferentiated heavy lifting and significantly improve their scale that they can support so that database could grow with their business requirements. So here is an example architecture for such use cases that we see across many customers in that category. They have these gateway devices that are serving the video streams that are collecting this data. The data is coming into Kinesis. Then they are using Kinesis data analytics to compute some aggregates on it and do time binning, windowing. And then they write the data into TimeStream. And then they are using TimeStream's Grafana connectivity to display some of these dashboards. The previous dashboard, for example, that I showed was using Amazon Managed Grafana. You could also have your own like self-hosted Grafana if you so desire. And you could connect to TimeStream to create these powerful visualizations to get your real-time as well as historical insights. Another customer is using energy storage management and for monitoring a fleet of energy meters. These energy meters are IoT devices that are emitting data using standard IoT protocols, for example, OPC UA, OPC DA, MQTT, et cetera. So in this specific use case, they are coming in through AWS's IoT services, which also integrate with TimeStream. And then once the data is in TimeStream, they can use the flexible SQL, the time series functions to perform insights using QuickSight. They can use SageMaker to do predictive maintenance and so on. And this is not just limited to energy meters. We have customers monitoring traffic lights. We have customers monitoring energy exercise equipments and so on. So here is an example architecture where these devices are talking to IoT Greengrass. Through IoT core, they are sending the data into TimeStream and then using QuickSight for their analytical dashboards. QuickSight is natively integrated with TimeStream, or using SageMaker to do predictive maintenance. Another use case is in media intelligence analytics. So we have a customer who performs media intelligence on brands and entities. For example, you have a brand, you have a product, you have a, let's say, a celebrity. These are all entities, and people reference them in their social media interactions. So they track these engagements to identify what are the sentiments associated with a specific brand or a specific entity that they are tracking. They crawl the social media interactions like tweets, pins, et cetera, and using their custom business logic, they are converting it into time series metrics. And then once the data is in TimeStream, now they can track day over day, hour over hour, week over week trends, any anomalies. So let's say there was a new launch. The customers are not perceiving it well. The brands can know it in real time that how the customer perception is changing. So this is another architecture. They have a much more bespoke architecture that they are using, where they have their crawlers. Then they go through a social content processing engine that is converting these social media interactions into time series data. And then they're writing that directly to TimeStream. So this is one of the cases where you don't need to come through any of the other services. TimeStream's Write SDK allows you to automatically and auto-scale ingest gigabytes per second. So you can come directly to TimeStream if that is your use case, write directly to TimeStream, and benefit from the scalability and the durability properties of TimeStream's ingest. Similarly, on the query path, they're not using any of our standard integrations, but they're using the flexibility that TimeStream supports through a broad set of SDKs. So we have support for Java, Python, Node.js, and Go, and several other languages. Node.js is popularly used for creating many of those, the visualizations within the browsers. And they are using these custom things as well as there is a JDBC driver that TimeStream supports so that it integrates with many of the standard visualization tooling that is based on JDBC. And they are using this flexibility to create a bespoke visualization platform to analyze their trends or to detect anomalies. The last use case is a monitoring, is an energy production use case where an US onshore oil and gas production company is modernizing their SCADA and historian systems by moving the management of this into the cloud. So this is a bigger picture of a bigger architecture. So here is where you will see multiple different services are coming together to address what the customer's use case is. The data is again from their on-prem SCADA and historian systems. It's coming in through either IoT services or through Kinesis, hitting TimeStream for their time series use cases. They are using Redshift for some of these use cases. So you can create a broader lakehouse architecture where TimeStream plays its part in managing time series data. So you can stitch together these bigger architectures and solutions. So let me quickly walk you through some of the overview of TimeStream to say why it gives you the properties of the purpose-built aspects that I've been talking about. So at a high level, what you will see is TimeStream has a decoupled architecture where ingestion, storage, and query scales independently. You're writing data through write endpoint, you're reading from the query endpoint, and all of the resources independently scale. It's replicated, it's highly available, and durable as well. So the data is replicated in TimeStream across multiple AZs so that it gives you the durability as well as the high availability. Data deduplication is automatically handled in TimeStream. So how many times have you spent energy debugging a query just because there was duplicate data that was sent out because of some error? Not a problem with TimeStream. It's built in. And no need to provision and configure resources. The different storage tiers, they are also independently scaled because some customer may have terabytes or petabytes or exabytes of data in the magnetic store. Memory store has different characteristics and different requirements. And the memory store is designed for fast point-in-time queries and high-throughput durable ingestion. The magnetic store is designed for high-performance analytical queries and cost-optimized longer-term data retention. And then you have another layer, which is your query engine, which is using a custom indexing layer to figure out where your data is. It is accepting your SQL queries, determining how much data you are going to process, dynamically allocating resources depending on your data processing needs, and then going and analyzing this data in parallel. And TimeStream automatically indexes and partitions your data, so no need to configure indexes, no need to configure partitions. Everything is just managed for you. So at the crux of this, you will see is what is the automatic partitioning algorithm that TimeStream is using. So in this figure, I'm giving you a conceptual view of a table in TimeStream. A table in TimeStream is just a logical resource. What you see here is time on the horizontal axis and a hash on the vertical axis. These hashes are computed from the attributes that you specify, the dimensions, measure names, etc. And we take this 2D space, and depending on where ingestion is happening, depending on how your data distribution is, we dynamically partition each of this. We dynamically partition this space. So what you are seeing on the right-hand side is partitions that are in memory store. On the left-hand side, partitions that are on the magnetic store. And TimeStream automatically repartitions, moves your data as it ages from the memory to magnetic store. And this entire partitioning is stored in our purpose-built indexing layer that allows us to quickly figure out what are the partitions that are relevant to a query. So when a query comes in, again, it has predicates on time, it has predicates on dimensions, and etc. So that translates again into a 2D bounding box. And now what we are doing is we are finding an intersection of what is the data that is relevant. So you can have a table with a petabyte of data that's storing 10 years worth of data. And if you have a query that touches the last 5 minutes of data, we are going to, within a few milliseconds, figure out what is the partitions that are relevant. So it doesn't really matter how much data you have in your table. The 5 minutes is what is relevant to you, and we quickly go to that partition in a matter of milliseconds. To show some of this scaling in action, so this is a blog that we published. You can search for it. We are using the DevOps dataset that I've been talking about, where, again, here we are focusing on scale and performance. So you will see these numbers are on the higher end, where we are ingesting about 156 million to 3 billion data points per hour, tracking between 1 to 22 terabytes of data per day. And these tables have been running for months. So you can think of some of these tables are already at the petabyte scale. And we are monitoring 2.6 million to 104 million time series. What you will see in this figure is 3 different types of queries. The cheaper queries are your interactive queries going over the last 10 minutes, 5 minutes, 1 hour of data. Then if you look at each of these cluster of blocks, there are these the vertical bars. The first 2 bars are those interactive queries. The second 2 bars are your dashboarding queries going after hours of data, and this is going over your raw data, not using the scheduled query feature. And then you have your analytical queries scanning days worth of data. And the different clusters of these graphs correspond to 3 different scale factors, starting from 1 terabyte per day to 22 terabyte a day. Now, there are some key aspects to take away from this figure. The first is that the cheapest queries, they are running in hundreds of milliseconds. So that gives you the interactive latencies in your dashboards, even when you're going over your raw data for the most recent data time ranges. Then as you go from left to right, the amount of data that the queries are touching are growing. But if you compare these graphs, you will see in some cases the data volume grew 22x and the latency did not increase much, or it increased in a significantly sublinear fashion. And that is the benefit of the scalability characteristics of TimeStream, where when a query comes in, looking at these partitions, we understand how much resources are needed, and the more data your query scans, the more resources we allocate to it. And that's how we are able to scale better and keep continuing to scale as your application or your data volumes grow. So if you think TimeStream fits your use cases, there are various easy ways to get started with TimeStream. You can just get familiar with it, go to the AWS Management Console. There are sample databases, sample queries to give you a feel of what TimeStream is. There are different integrations with Kinesis, IoT Core. If you are using Telegraph, like InfluxDB for the tick stack for doing tracking your DevOps metrics or customs metrics, we have a Telegraph adapter. We have several tooling integrations with JDBC, Grafana, QuickSight, some of these that I have covered. And there are video tutorials and best practices to help you optimize your data model as well as your queries. So in summary, TimeStream is a purpose-built database built from the ground up to give you fast, scalable access to time series data at any scale. No servers to manage, no data lifecycle related responsibilities. You get purpose-built time series functions, flexible SQL query characteristics in a database that is durable, highly available, and secure from the ground up. Thank you very much. Feel free to reach out to me. I have my Twitter handle included here. And please complete the session survey. Thank you very much.